Ladies and gentlemen, welcome to Geometry. I'm absent again, and one thing I hate to be is absent. I've got these kids at home that keep getting sick, so I apologize for not being here. This is a kind of an easy section to have to work on while I'm not here because of things that should be reviewed from your Algebra 1 course and should be related to what you did for homework last night. So the first thing I'm asking you to look at is ratios and proportions. It's sort of an introduction to this next chapter. We're going to have three figures or two figures, maybe triangles. Typically they're going to be triangles. It could be any shape, and they're going to be similar to one another. And the word similar is a geometry word. It doesn't mean the same. It means they have specific properties on here which relate to angles and size. So if you look at the side lengths on your paper, these are drawn to scale on your paper. You know, this is a 30 by 20 rectangle. Label those two. This is a 15 by 10 rectangle. And the last one is a little guy, is a 6 by 4 rectangle. And they are drawn to scale on your paper. That's why that one on the right is so small. One thing we'll talk about is a scale factor. And if you look at this, this has been scaled down. And most of you can see this is scaled down by half of the size, or a 2-to-1 scale. It's another way to say that. Sorry. We'll also talk about the scale factor of white to blue. Yes, those are patriotic American colors. You know, the scale from here to here, you might realize it's being divided, and it might take a minute to think about that. How is it being divided? It's not half the size, it's less than half the size. And you might realize this is 2.5 times smaller. Or if you took these dimensions and multiplied that by 2.5, you get the height. If you multiply the width by 2.5, you get the new width on there. So, two questions to think about. One is there anything congruent about the rectangles, which came up a second ago? And when we talk about this word similar or proportional in size, the angles will be the same. So whether these were triangles or hexagons or some other shape, they'll be proportional in size. In other words, the sides will have some weird ratio going on, or some common ratio, but the angles will be congruent, which we'll talk about more throughout the chapter. And then this question, how could you describe them? The word is similar, and it's a specific geometry word, meaning the angles are the same, but the sizes are, proportional. And there's the symbol for similar. That's the little squiggle that goes over the congruent sign. That's why it's going over a congruent sign, or over an equal sign. It means the shapes are the same, but the sizes could be different. And we usually say it's proportional in size. So, like I mentioned a minute ago, you could call this a 2-to-1 scale or a 1-to-2 scale. I want to talk about scale factors throughout the chapter. And then, of course, this one to this one, you could just write a ratio, a 10-to-4 ratio, and reduce that, and it would reduce to a 5-to-2 ratio or a 5-to-2 scale. So you'll see us do this with fractions. You'll see us do this with the colon on there. You know, if you took 15 over 6 and reduced it, you'd get 5 over 2. And the same thing with 10 over 4. So proportional sizes. So I'm going to kind of skip around and do most of what's on your notes here. The first thing I want to define is just define the word ratio. So a ratio is a blank of two numbers. Well, it's just a comparison. It's comparison by division, if I want to be more specific. You sometimes see it written A to B with colons on there, or A over B, and they mean the same exact thing. So you should be able to go back and forth interchangeably between words, A to B, or the colon, and then the fraction on there. A fraction is a ratio. So eventually we'll talk about these Matryoshka dolls. I'm going to skip this example since I'm not in class, and I'll come back to that. But we will jump to maybe the strength to weight ratios here. So I've got these three, take a minute and read that to yourself, and then label the weights of the actual bars. This is a 40-pound steel bar. This is a 30-pound wood bar, so it's a little thicker, as you can see, but weighs less because it's wood. And this weighs the least of all. Aluminum is a very light material. And then on top of it, I want you to label these weights that we're stacking on here. This is an engineering concept. When they say strength to weight, the strength is how much it takes to fail something. So if you imagine Paul Marshall with 1,000 pounds on top of him, he might fail. This is Paul Marshall's strength. These numbers are his strength. How much weight he can actually hold. The weight ratio here is the weight of the actual physical bar. And they compare those two things. When engineers are comparing bridge materials, Do they use steel? Do they use wood? Do they use aluminum? They pick those partially on a strength to weight ratio. So there are 3 different answers I hope you can get here, and then compare which one of these materials has the best strength to weight ratio. So it's a good time to pause, label everything, and see if you can write a ratio for each of these 3, and then compare those 3 ratios. Hopefully you get to a point where you go, okay, well, this is a 75, because I'm tripling this, to 40 ratio. And you always want to be in the habit of reducing ratios when you're just answering as a ratio. So 5 goes into both of those. You can divide that down to 15 to 8. And you can't go much more than that. The second one, of course, is a 50 to 30 ratio. And, of course, you can divide them both by 10 and get a 5 to 3 ratio. And the last one, this little weight here, is 10 plus the 2 25s. You get 60 to 24. You can divide all those by 2. You can divide them all by 4. You can divide them all by 12. And get it down to 5 to 2. So in the math world, we love these ratios. In the engineering world, they want to know which one of these is the best. And that's where decimals are a little more helpful. So if you wanted to turn any one of these ratios into a decimal, you just type in 15 divided by 8, and you get a decimal. And that tells you how strong it will be relative to its own size or weight. So this one is almost a 2 to 1 ratio. It's almost 16 to 8. This one, 5 to 3, is kind of close to 2 to 1. And this one's greater than 2 to 1. Like I said, if you calculate those with a calculator, you get approximately 1.87. 5 divided by 3 is 1.6. So the steel is actually better than wood. And the last one is a 2.5 to 1 ratio, exactly, actually. Which is the reason aluminum is often used for materials. The drawback to it is it's very expensive. So the decimal, I just showed the decimal in here to show you a practical side of it. And where it comes from dividing the ratio on there. So these are both correct answers. This would be like 1.87 to 1 ratio, or a 1.6 to 1 ratio. Tells you how strong a material is relative to its own size or weight. Try these 2 out on your paper, and I'll be back in a minute in the next part to kind of see if you've got an idea. We've done something like this recently. See if you can get some equations that you can solve. Go for it.